For the first one, I will explain about the celestial equator and the ecliptic. But I will use this dome to represent the celestial sphere, which is an imaginary sphere surrounding the Earth. This line represents the Earth's rotation axis. And the points where the axis meets the dome are called the North Celestial Pole and South Celestial Pole. And this yellow line around the middle of the dome is the celestial equator. It is the projections of Earth's equator onto the sky. And the blue line is the ecliptic. It represents the apparent path of the sun across the sky during 1 year. The ecliptic is tilted by about 23.5 degrees relative to the celestial equator because Earth's axis is tilted. And the 2 points where the ecliptic crosses the celestial equator are called the equinox. And next, I will explain about the equinox and the solstice. For the first one, vernal equinox. At the vernal equinox, the sun is located on the celestial equator. Daytime and nighttime are approximately equal, about 12 hours each. And the sun rises exactly in the east and sets exactly in the west. For the second one, summer solstice. At the summer solstice, the sun reaches its maximum positive declination, about 23.5 degrees. In the northern hemisphere, daytime is the longest and nighttime is the shortest. The sun rises in the northeast and sets in the northwest. For the third one, autumnal equinox. At the autumnal equinox, the sun crosses the celestial equator again. Daytime and nighttime are equal in length, and the sun rises in the east and sets in the west. And for the last one, winter solstice. At the winter solstice, the sun reaches its maximum negative declination, about minus 23.5 degrees. And in the northern hemisphere, daytime is the shortest and nighttime is the longest. The sun rises in the southeast and sets in the southwest. In summary, Earth's axial tilt caused the sun to change its position along the ecliptic, resulting in seasonal change in day length and the sun rising and setting direction.
Next, we're going to talk about reference point and plane of equilateral coordinate system. This system uses the celestial equator as a main reference plane, and it is the projection of the Earth's equator onto the sky. The reference point is the vernal equinox here, where the sun crosses the celestial equator from south to north. Right ascension or RA is measured along celestial equator starting from vernal equinox at 0 hour to summer solstice 6 hour, autumnal equinox 12 hour, and winter solstice at 18 hour and go back to vernal equinox at 0 hour. And declination or depth is measured north or south of the celestial equator similar to latitude, and it is measured in degrees, like 30 degrees to the north, 60 degrees to the north, 90 degrees to the north, or 30 degrees, 60 degrees to the south. Next, I will explain how to identify the declination of this star using the horizontal coordinate system. First, we have to use this coordinate system, which is the horizontal coordinate system. And when the star rises from east, and then up to the maximum altitude, we can see that this star is perfectly at his head. So this star has the maximum altitude at 90 degrees. And since we are at Geneva, which is at 46 degrees north latitude, we're gonna sum the maximum altitude of the star plus with the latitude that we are, and then minus 90 degrees. So we're gonna get the declination. So 90 plus 46 and then minus 90, we can see that the star has 46 declination, which is actually 46 declination here. To be more challenging, I'm gonna change the star, randomly locate the star here. First, we have to use this coordinate system, which is horizontal coordinate system. We're gonna rotate the sky to make this new star at the maximum latitude. Up, go up, and then it maximize here. At this position, this star is likely 60 degrees of altitude based on this horizontal coordinate system. So since we are at Geneva 46 degree north, we're gonna sum 46 with 60, which is 106, and then minus with 90, so we're gonna get 16, and this star is at 16 declination here. So this is the example that we can convert the coordinate from horizontal to equilateral coordinate system. But if you notice something, if I place star here near the axis of rotation, we can see that the star never fall below the horizon. This star here remains above the horizon. It never go below this point, and this star is called circumpolar star, or the star that never sets below the horizon. But if I place this star some kind of below, we can see that it sets below the horizon. And how we can calculate this one? To calculate the declination of this kind of star, we can calculate by using 90 degree minus our latitude. For example, we are at Geneva, we are at 46 north latitude, so we calculate 90 minus 46, which is 44, meaning that any star with the declination larger than 44 is gonna be circumpolar star. Let me show you. If I place the star here at 60 degree of declination here, and then when we rotate here, we can see that the star never goes below the horizon. And if I place the star below 44 degree of declination, for example like 15 declination here, we can see that the star will have some time goes below the horizon. In this video, we show how celestial sphere help visualize the sun and stars trajectory from different locations of the world. Thank you for watching.